Welcome to UGC lecture series BSc Physics Honors Semester 6 Statistical Physics Lecture 9. In this lecture, we are going to deduce Rayleigh-Jeans Law, Wien's distribution law, Wien's displacement law and Stefan-Boltzmann law from Planck's law, then summary about all these concepts. In the previous lecture, we learned how to get the Planck's distribution law. That Planck's distribution law says the total energy density within a wavelength range, within a frequency range. So, the Rayleigh-Jeans law can be derived from the Planck's distribution law or Planck's quantum theory. This Rayleigh-Jeans law was a useful but not completely successful attempt at establishing the functional form of the spectra of thermal radiation. In statistical physics, many work has been done regarding the thermal radiation. Bose-Einstein statistics, Maxwell-Boltzmann statistics, these are all statistics which explains the number of atoms present in each energy level. Each energy level is assumed as a function of temperature. When the temperature increases or decreases, number of atoms present in these energy levels is given mathematically by Maxwell-Boltzmann, Bose-Einstein. So, these are all called statistical physics. That statistical concepts can be used to explain the radiation law in statistical physics. That radiation law is very much explained by Planck. From Planck radiation law, Rayleigh-Jeans law can be derived. Before the proposal of Planck's law, Rayleigh-Jeans law was derived, but after the proposal of Planck's law, from Planck's law also Rayleigh-Jeans law can be derived. That is what we are going to see in this lecture. So, Rayleigh-Jeans law stated a useful explanation in thermodynamical physics, but that useful explanation was not complete to establish the functional form of the spectra of thermal radiation. He said that the energy density per unit frequency interval at a frequency nu is given by u nu is equal to 8 pi nu square kT by c cube, where nu is the frequency of the thermal radiation assumed, k is the Planck's constant, T is the temperature, c is the velocity of thermal radiation. By knowing all these things, you can Planck's has derived a radiation law. Now, this can be derived using Planck's law. For that, we should know the Planck's law. Planck's law can be stated as a function of frequency as well as a function of wavelength. Here, Rayleigh-Jeans law is given as a function of frequency. So, Planck's law also should be taken as a function of frequency. In that Planck's law, E nu is equal to 8 pi nu cube by c cube into h nu by e power h nu by kT minus 1 is the radiation density or energy density. In that, that kT and h nu are related, because h nu is also energy, kT is also energy. H nu is the quantum mechanical energy, kT is a thermal energy. This quantum mechanical energy and thermal energy disobey when the frequency increases. So, in that case, this Rayleigh-Jeans law can be derived. So, first let us take the Planck's quantum hypothesis. E nu d nu is equal to 8 pi nu square by c cube into h nu by e power h nu by kT minus 1. This is the Planck's hypothesis. Here nu is equal to c lambda, c by lambda. So, if you substitute this, that d nu can become d nu by d lambda into d lambda, which is equal to c by lambda square into d lambda. So, we got d nu as a function of d lambda. In this expression, that d nu is equal to d nu by d lambda into d lambda. So, we got c by lambda square into d lambda. So, the energy density as a function of lambda and t can be written as 8 pi hc by lambda power 5 into 1 by e power hc by lambda kt, hc by lambda kt minus 1. So, this is the Planck's radiation law or distribution law in terms of wavelength. Now, we are going to deduce Rayleigh-Jeans law from this Planck's distribution law. So, let us substitute, let us take the component h nu by e power h nu by kt minus 1. Let us take this component. In that component, longer wavelength region or smaller frequency, longer wavelength or smaller frequency, we have got that kT is very greater than h nu, thermal energy, quantum energy, very higher than h nu. So, that we got that e power h nu by kT can be written as 1 plus h nu by kT in terms of the binomial expression. E power x is expanded, only the first two terms are kept. So, we got e power h nu is equal to e power h nu by kT is equal to 1 plus h nu by kT. So, Planck's law will reduce to u of nu comma t is equal to 8 pi nu square by c cube into h nu by e power h nu by kT minus 1 if that kT is very larger than h nu, then e power h nu by kT can be substituted as 1 plus h nu by kT. So, instead of this we can substitute 1 plus h nu by kT. So, you will get u of nu comma t, that is the energy density as a function of frequency and temperature, is equal to 8 pi nu square by c cube into h nu by e power h nu by kT minus 1 will become 8 pi nu square by c cube into h nu by 1 plus h nu by kT minus 1. Now, this plus 1 and minus 1 gets cancels. So, this can be further simplified as 8 pi nu square by c cube into h nu by kT. So, in a fraction the denominator has got another fraction. So, that can be further inverted. So, the expression will become 8 pi nu square by c cube into h nu into kT by h nu. So, this h nu gets cancels. You got 8 pi nu square by c cube into kT. So, this is the energy density as a function of frequency and temperature. This is the Rayleigh-Jeans law. Rayleigh-Jeans law. So, Rayleigh-Jeans law can be deduced from Planck's quantum theory of radiation by assuming that kT is very greater than h nu at smaller frequencies. So, instead of that e power h nu by kT, we can substitute 1 plus h nu by kT. So, the expression will reduce to 8 pi nu square by c cube into kT. So, that will give the Rayleigh-Jeans law. Then Wien's radiation formula. Using Planck's concept, you can deduce Wien's radiation formula or Wien's distribution law. Wien's displacement law is different from Wien's distribution law. So, Wilhelm Wien in 1896, before the proposal of Planck's quantum theory, derived theoretically on the basis of thermodynamical principles a black body radiation distribution law to fit the experimental data. Here, Wien derived the distribution law as u of nu comma t is equal to 4 pi nu cube by c cube b into exponential of minus a nu by t. This is the Wien's distribution law. The same concept can also be derived from Planck's law. So, that is the success of Planck's quantum theory. This Planck's quantum theory, as I said earlier, is applied in all areas of physics. The very important application of this Planck's quantum law is photoelectric effect, which is a very useful phenomena in modern physics to explain the operation of solar cells. Photoelectric effect is given by Albert Einstein. He assumed the light as a wave, as a radiation. Energy possessed by that radiation is h nu. That h nu radiation is given to the electron present in the material which receives the radiation. That electron receives the radiation and excites. So, when it excites, it starts moving. So, when electron moves, conduction takes place, we get current. So, this is the success of Planck's quantum theory. Using this Planck's quantum theory, we can derive Wien's radiation formula also. How it can be derived? Let us see how it can be derived. Now, this Wien's distribution law is in the lower wavelength range. In the lower wavelength range. Now, you know Planck's radiation law, u of nu comma t is equal to 8 pi nu square by c cube into h nu by e power h nu by kT minus 1 is the Planck's distribution law. To get Wien's radiation formula in terms of wavelength, so u of lambda comma t is equal to 8 pi h c by lambda power 5 into 1 by e power h c by lambda kT minus 1. So, here just substitute that h c by kT is very greater than the wavelength. So, if this h c by kT is very greater than wavelength, so we got h c by e power lambda kT is very greater than 1. So, that the energy density in terms of wavelength and temperature can be written as 8 pi hc by lambda power 5 into 1 by hc by e power lambda kT. This is the energy density in terms of wavelength. When we assume hc by kT is very greater than lambda, then automatically that hc by e power lambda kT is very greater than 1. So, the energy density as a function of wavelength and temperature will become 8 pi hc by lambda power 5 into 1 by hc divided by e power lambda kT. Now, this expression is similar to Wien's distribution law for constants C1 and C2 as follows. That is, energy density as a function of wavelength and temperature is equal to C1 by lambda power 5 into e power minus C2 by lambda t. So, by taking C1 and C2 as constant, the previous expression rho of lambda t is equal to 8 pi hc by lambda power 5 into 1 by hc by e power lambda kT is similar to the expression rho of lambda t is equal to C1 by lambda power 5 into e power minus C2 by lambda 2. So, we will get the Wien's distribution law as rho of lambda t, that is energy density as a function of wavelength and temperature, C1 by lambda power 5 into e power minus C2 by lambda t as the Wien's distribution law. This is Wien's distribution law. You can deduce Wien's displacement law. That Wien's displacement law talks about the product of maximum wavelength and temperature is equal to a constant. You know, in black body radiation emission, the energy density or intensity of the radiation is plotted as a function of wavelength. So, you know, when the wavelength will be, the graph will be like this. Energy is density is plotted in y axis, then wavelength is plotted in x axis. So, you will get a graph like this for a particular temperature T1. As you deduce or reduce the temperature, then the maximum wavelength will maximum intensity will come down. As you reduce the temperature, the maximum intensity will further come down. This is the graphical explanation of black body radiation. In this thing, the product of maximum wavelength and temperature is equal to a constant. This gives the Wien's displacement law. As you increase the temperature, as you if T1 is the maximum temperature and T2 is the next lower temperature and T3 is the next lower temperature, means as you increase the temperature, then the wavelength will be shifted to lower wavelength. Lower wavelength sense here. So, this will be the lambda m for the thing, and the temperature reduces. So, this will be the lambda m for temperature T2, and this will be the lambda m for temperature T3. This is Wien's displacement law. Now, let us see how this Wien's displacement law can be deduced from the Planck's radiation law. You know Planck's radiation law, which is rho of lambda t is equal to 8 pi hc by lambda power 5 into 1 by e power hc Hc by lambda kT minus 1. This is Wien's Planck's distribution law in terms of wavelength. Now, according to the Wien's displacement law, rho of lambda comma T maximum, where lambda is nothing but lambda maximum, and the rate of change of energy density with respect to the wavelength is equal to 0. Now, find the rate of change of energy density. This is energy density. Rho of lambda t is equal to 8 pi Hc by lambda power 5 1 by e power Hc by lambda kT minus 1. This is energy density in terms of wavelength. Now, this is differentiated partially with respect to wavelength. What expression will get is will get rho dou rho by dou lambda is equal to minus 5 by lambda power 6 into 1 by e power Hc by lambda kT minus 1 minus lambda square kT by lambda power 5 into e power Hc by lambda kT minus 1 the whole square is equal to 0. D dou rho by dou lambda is equal to 0. This is the mathematical expression we get after differentiating that rho as a function of lambda and t with respect to lambda. Now, further simplification of this gives by taking that minus 5 by lambda power 6 into 1 by e power Hc by lambda kT minus 1 minus lambda square kT by lambda power 5 into e power Hc by lambda kT minus 1 the whole square is equal to 0. So, now 5 is equal to Ch by lambda kT into e power Hc by lambda kT over e power Hc by lambda kT minus 1. Simplification of this expression will give this one. Now, let the Ch by lambda kT as alpha. So, let Ch by lambda kT as alpha. So, the above expression reduces to e power alpha is equal to 5 by 5 minus alpha. Now, remove this alpha by taking logarithm. So, alpha is equal to natural logarithm of 5 minus natural logarithm of 5 minus alpha. So, this the transcendental equation can be solved graphically or numerically to obtain the Wien's displacement law. So, we will get lambda mt as a result of this transcendental equation. This can be solved either graphically or numerically to get Wien's displacement law. Now, numerically the value of this lambda mt is obtained as 965, which is equal to alpha is equal to Hc by lambda maximum, that is the wavelength at the maximum energy intensity into kT is equal to 4.965. So, we will get the value as lambda t is equal to hc by k into 4.965, where h is Planck's constant, c is the velocity of light, k is Boltzmann constant. So, if you substitute all the values of the constant, we will get lambda m into t. So, h is 6.625 into 10 power minus 34 joule second. Then c, velocity of light, 3 into 10 power 8 meter per second. Then Boltzmann constant. So, we will get that lambda maximum is lambda mt is equal to 2.8977 into 51 into 10 power minus 3 meter Kelvin is the value we got about this lambda mt. So, using this you can deduce the Wien's displacement law. So, using Planck's radiation law, we learned how to get the Wien's displacement law. So, in this lecture we learned how to deduce Rayleigh-Jeans law from Planck's law, then how to deduce Wien's radiation law from Planck's law. Rayleigh-Jeans law talks about the radiation density, and that Rayleigh-Jeans law classically explained the black body radiation. Wien's displacement law proposed after Rayleigh and Jeans. So, Planck's black body radiation law can also be used to get Rayleigh-Jeans law. That is what we learned in the first part of this lecture. Then we learned how to get Wien's distribution law. Wien's distribution law is also similar to Wien's radiation law. Then we got that. Then Wien's displacement law, lambda m is the thing about Wien's displacement law, are the concepts we learnt from this lecture. After listening to this lecture, you can answer the following question: state Rayleigh-Jeans formula, state Wien's radiation formula, state Wien's displacement law. Thank you.